Hello everyone, welcome to lecture 16. In this lecture we're going to talk about CPG force. Okay, so the question is, when you have a downward water flow or upward water flow, will it change the effective stress? I think in the previous lecture we talked about the head, so pressure head and elevation head and the total head. And the total head is conserved because of the energy conservation. And when the total head is conserved, total head is sum of the elevation head and the pressure head. So today in this lecture, we're going to talk about then from there, when you have a water flow like that in the steady state flow, what will be the change in effective stress? Or before that, what will be the change in pore pressure? So therefore, what will be the change in effective stress? Let's see an example here. So here, when you have rain, so for example, when there's no rain, then slope is stable, like as we cut. And when there's rain, the water flow over the ground surface, and also it kind of infiltrated to the soil, and it can flow because of the gravitation. And this downward seepage flow often causes landslide or slope failure. So we can see, kind of imagine that the water flow has some effect or mechanical effect as an external force to the soil grains. What about the excavation site? And here, when you excavate, because from outside the water will flow to the inside of the excavation site. So then outside this wall you have a downward water flow, and inside you have an upward water flow. So how does the direction of the water flow affect the pore pressure and therefore the effective stress? If the water flow is too fast, you can think of like boiling the sand. So if the water flow is too fast, then this very top surface soil will be destabilized, and it can be also failed and can reach to failure. And when the effective stress is 0. So when there's no effective stress, that means that there's no granular stress between that. So they're not touching each other, that they don't transfer any force. So it's kind of, their individual grains are free without any bounding force. That's when happens when the effective stress is 0. So overall, the force exerted by the water flow and acting on the soil grain is called seepage force. And this seepage force affects the effective stress. We'll see whether we can quantify it. So let's look at this diagram. This kind of looks complex, but you have a soil in here, in a reservoir, in a container, and it's all filled with water. So water is filled up from here up to the pipe. And you can control the pipe height. So you can bring up and you can bring down, so that you can control the level of the water levels with this water reservoir at the right side. So then when the water level is at the level of E, which is the same location with the here right side water reservoir, then head difference is 0. So you're perfectly balancing the water level, left and right side. So then there's no flow because there's no head difference or energy difference. And if you lower down this one, then the E, so when the water level becomes lower than E, so then water will flow this way, right? Because the water level is here at the outlet. So this becomes the outlet and this becomes the inlet then. So here the water level, when you think about the head difference between here and here, H becomes negative. And the other way, the other case is that when you elevate, when you bring up the pipe, so that the water level here becomes at the level of H on F. So now the water level is higher than the E. So then H is positive. So the flow will occur this direction. Right? So in terms of the, when you look at the flow from the perspective of the soil, then in this case, when the water flow from left to right, you have an upward flow. If the water flows right to left, then the water goes here, so that you have downward flow. Okay. So let's think about the head then. At the bottom of the soil and the top of the soil at B and C. First, at B, the rule is that when you have an exposed water surface, the pressure head is 0, right? And you can set the datum at the lower water surface here. So the H, at A, the HE will be also 0. So then at B, because it's the location is minus HW, so the elevation head will be minus HW. And pressure head is because of this water height, you have HW. So total head is what? Summation of HE and HP. So this is HE plus HP. So this becomes 0. Okay. And what about C here? You have to think from here, right? So then at F, elevation head is H, and the pressure head is 0. So total head is H. So then this total head will be conserved to the bottom of the soil. So you have a H here. And we know that the pressure, so the elevation difference, elevation head is minus HW minus L. So then from this and this, you can compute that pressure head is H plus HW plus L from the conservation. So from this relation, because you know the H, HT and the HE, you can compute the HP. So then pore pressure can be computed, can be calculated using the pressure head. So pore pressure is always HP times gamma W. So here HW times gamma W will be the pore pressure at B here. And at C, the pore pressure will be H plus HW plus L times gamma W. So then this component, when you look at the pressure, pore water pressure, H component is the seepage component. If the water is not moving, let's say that you have a valve here, then at C, the water pressure will be HW times L times HW plus L times gamma W, right? So if the water is static, so if the water doesn't move, the pore pressure will be just HW plus L times gamma W. And when you compare this one from this one, you have a H in addition to this static water pressure. So that's the difference when you have a moving water and the water doesn't move. Okay, so here the total head determines the water flow direction. So whether as you bring up the water pipe on the left side, or lowering down, it will determine the water flow direction, and pressure head determines the pore water pressure. And then, because we know the pore water pressure here, we can determine the effective stress at sea. So let's do that. Let me zoom out. Total stress at the bottom of the soil here at sea is the total stress sigma is HW times rho W times G. So that's the weight of this water column over the soil. And here L times saturated density rho Z times G. This is the weight of the saturated soil. And pore pressure at sea is what? U is H plus HW and L times rho W and G. So then let's get the effective stress from sigma minus U. So here rho Z L G plus HW, rho W and G minus, this is the total stress from here, and HW H HWL and G, and then you can see that this term is this, so it will cancel out. So rho Z minus, and we can combine the L. So here the effective stress term, when you look at the effective stress, this is the seepage component. So if the H is positive, the effective stress is decreased, is reduced by the water flow. That means that if the H, again H is positive, sigma prime goes down. So then H is positive means that it's upward flow. If the H is negative, which means the downward flow, then effective stress goes up. So depending on the direction of the water, it will change the effective stress. And overflow, effective stress decreases, and downward flow, effective stress increases. If you have an overflow, as the H increases, at some point, because the total stress is constant, and with the increasing H, this pore pressure increases, at some point, this effective stress can go to zero, right? So if H increases infinitely, then it will cancel out this one, so that it's gonna be zero. And it's called the quick condition, where we define where that stage is defined as the failure. So as the H increases, at some point the sigma prime goes to zero, and this means the grains have no intergranular stress. So now they're gonna play a part. And it's called a quicksand condition or boiling condition. Soil does not have shear resistance and it flows like liquid. So in the soil mechanics and in geotech, we want to check when this kind of a quicksand condition or the quick condition happens. So we estimate the factor of safety against the quick condition. When the factor of safety is less than 1, we expect that quick condition will occur, which we don't want. And if the factor of safety is higher than the 1, then the quick condition will not be will not occur. So when the from the previous equation here, from this previous equation, we can set the effective stress is 0, and then we can find the H that caused the effective stress becomes 0. So here, when the effective stress is 0, then rho set minus root of GL minus H times G times root of is 0. So then from that, H over L is rho set minus rho W and rho W. And this is fundamentally the submerged density over water density. And it's called the critical hydraulic gradient. So when the H, the head difference over the length of the certain length of soil is bigger than the HC, which is the rho sub minus over rho top, then the quick condition will occur. So the effective stress will eventually become 0. And this HC is called the critical hydraulic gradient, and rho prime or rho sub over rho W, and this is saturated density minus water density over water density. And you can see that this is the critical hydraulic gradient depends on the soil property only. And if we plug the equation that we learned in the chapter 2, then this IC is merely function of GS and the void ratio. And GS is, it has a very narrow range, so we can assume 2.7. Then with different void ratio, critical hydraulic gradient ranges from 1 to 1 to 0.84. So in average, critical hydraulic gradient of 1 is typically used to estimate the factor of safety or the safety against the condition, just to get the ballpark estimation. So the factor of safety, what about factor of safety? So factor of safety Fs is calculated as IC over I. So IC is the critical hydraulic gradient, which is given by the soil property, how the soil is well compacted, and over the hydraulic gradient of the configuration. So when this I is H over L, so that's given by the geometric condition in the site, at the site. Okay, so this is the same, just review in page. And if you look at the handout here, it has more details about the seepage, over seepage and downward seepage. And it has really good drawings also. So without the seepage, you have a static total stress and the pore pressure and effective stress. And with the overflow, you have this component, right? So pore pressure increases by H, so that the effective stress decreases by minus H times gamma W. So with the downward flow, with the total head difference H, you have an increase in effective, decrease in pore pressure, so minus H. And because of that, you have an increase in effective stress. So here you can see the minus H, and here is a plus H. Okay. So I hope you read this handout carefully when you review the lecture, and I'll see you in the real lecture. Thank you.